If fx equal to x raised to the power n, then f1 plus f prime 1 upon 1 factorial plus f double prime 1 upon 2 factorial plus and so on up to f1 at 1 upon n factorial is. So somehow we can write this function in a polynomial structure. Then we can use Taylor's theorem. Because of Taylor's theorem, somehow we give an idea to write a function in a polynomial structure or in terms splitting. So what Taylor's theorem says? Taylor's theorem says if function f is continuous and n times differentiable, n times differentiable over an over an closed interval x x plus h, this h is very small, then there exist some points between in this interval denoted by x plus theta h, and for this theta will belongs to open interval, or you can say closed interval 0 to 1, such that I can write function fx plus h equal to fx plus h f prime x upon 1 factorial plus h square f double prime x upon 2 factorial and so on up to h raised to the power n minus 1 f n minus 1 x upon n minus 1 factorial, and last term is h raised to the power n upon n factorial f n x plus theta h. This is last term. And we have to ask about to find the value of this expression, as you can see in the question. So if I put h equal to 1, then somehow I will get the structure as is asked. So first I will try to find derivatives of the function, because of we will use derivatives of the function in this. As fx equal to x raised to the power n, so f prime will be n x raised to the power n minus 1, f double prime will be n minus 1 x raised to the power n minus 2. Then doing differentiation up to n terms or n times, fn will be n minus 1 n minus 2 up to 1 x raised to the power n minus n times. So this value x raised to the power 0 is 1. So fn is n minus 1 and so on up to 1, and this is nothing but n factorial. So we have fnx equal to a constant function n factorial. So from this the last term was in the expression 1, this is expression 1. So you can see what is the last term. This is f raised to the power n x plus theta h. Because of this is a constant function, that's why fn 1 plus theta h will equal to n factorial, and you can see in the last term of the expression this is f raised to the power fn, means n times the derivative of the function at 1 upon n factorial. So somehow we have to replace this one, as you can see in circular part, in red circular part. So because of constant function, so I can replace Fn 1 plus theta h is Fn1 because of constant function. So the equation 1 becomes f of 1 plus or x plus h equal to fx. This will become fx plus h f prime 1 upon factorial 1 plus h square f double prime 1 upon 2 factorial plus and so on up to h raised to the power n f n1 and factorial. So if I consider the interval, because of we are talking about x and x plus h in this interval, if I consider a particular interval 1 to 1 plus h, means it will be fx, then 1 is playing the role of x, so f1 plus h f prime 1 upon 1 factorial plus h square f double prime. So in this equation x will be there, so f double prime 1 upon 2 factorial and so on up to this term also, and this one value is f1 plus h. Now put h equal to 1. If you put h equal to 1, then the asked inequality or equation we obtain f2 equal to f1 plus h f prime 1 upon 1 factorial and so on up to, because of h equal to 1, so h will not work here, because of fn 1 upon n factorial. So you can see this is the expression. We have to find the value of it. So and this value is equal to f2, and we will find this using given function fx equal to x raised to the power n. So put x equal to 2, so 2 raised to the power n. It means 2 raised to the power n will be our right choice. So which one option is giving 2 raised to the power n? So option first is correct.